Chapter 3, How Data is Transported Over Networks, Part 2. All right, so the second half of our lecture this week, we're going to be looking at some specific equipment that lives at specific areas in our TCP/IP model. Really what we're speaking about today, the router, right? The router, it lives natively at layer 3. Think about this for a minute. If it lives at layer 3, then what type of address does it deal with? What does it see? Well, if you answered IP addresses, that's absolutely correct. So routers are IP devices, Internet Protocol devices. What do? They do lots of stuff, but fundamentally, they do this. They join networks together, right? Look at the internet. That's nothing but a bunch of little networks all joined together to make this one ginormous interweb that we all know and love. That's made possible by routers. We also see the same thing inside our environments, because we can have multiple networks internal to our infrastructures. And if we're going to join them together, which we do want to, we'll have to have routers do that. Routers also join our internal environments to the external ones out there on the internet and those that are provided by ISPs. So what form do they actually take? Could you pick one out of a lineup? You've probably guaranteed you've seen one. If you have Time Warner or a DSL service or something like that, you certainly have. They are physical boxes, and they can range anywhere in size to these big core devices like you see here that are, these things are 8, 10, 12, 15 rack units in height. They can weigh hundreds of pounds, and they can carry price tags on them, hundreds of thousands of dollars. Right? This particular one would be like a core device in a large data center where I would have lots of networks that are being joined together, and I would be having lots of different functions going on and all that. Probably more commonly is I'm going to see a smaller type of router like right here. These are also found in data centers and server rooms, particularly in smaller organizations. They can also be found in wiring closets as edge devices, as ways of piecing the periphery of networks together. And they scale all the way down to a $100 device you could go and buy from Best Buy if you chose to. I mentioned Time Warner and cable modems and all that before. If you have a quote-unquote cable modem, what you really have is a router. So routers do all kinds of stuff. They also do things. They can reach outside of their native layer. That's actually called a firewall, and a firewall is really nothing but a souped-up router. Routers can also provide network monitoring, produce logging, reports, trigger alarms, all kinds of stuff. They can get quite fancy. They can be quite diversified. But at their core, a router is simply a device that connects networks together. Now we can break out routers in really a couple of broad categories. We have interior routers, which are the routers inside our environment. Right? If I have a multi-network infrastructure in my enterprise environment and I'm connecting them together, I may have one or more routers that's internal to us, that we're responsible for, that's only aware of our networks. We also have exterior routers. These are the routers that are outside of your environment. Commonly, these are the routers that are out there on WANs, wide area networks, the internet, that type of thing. And from here we can define the border router, which is a router that sits between an interior environment and an exterior environment. So how do routing tables do it? How do they join networks together? Well, they do it by connecting to them. Every time you see a router, you are seeing the border of a network, right? So right here's a network A, okay? Local area network A, and I know I'm on a point of demarcation because here's a router. And over here, network B. And I know I'm on the point of demarcation because here's a router. Well, routers sit on network borders. So not including the internet right here, how many networks do you think I'm looking at in this picture? Let's look. Network 1, right? That's it, or network A, there's one network. Network B, there's a second network. And here's a third network right here, the one that connects the two routers together. So I'm looking at 3 networks, not even including my internet connection right here. Every time you see a router, it is sitting directly on top of a border between 2 other networks. Routers also do this thing of trying to figure out what the best route through networks are, hence that term router. How do I get from point A to point B? Right? Well, it's the router that makes that decision. It's the one that keeps tracks of all my different routes, by paths for getting there. Maybe I can go this way, maybe I can go this way, that way, whatever. And they do it through something called a routing table. And the routing table is a dynamic database that routers keep in RAM that holds information about the paths to different locations. And that's really all that it is. They contain IP addresses out to network identifiers. Remember we were talking about IP addresses here in part 1? Part of your IP address identifies the network number, part of it identifies the host. Well, it's a network number that routers care about. They join networks and they have routes not to host, but to networks and to the networks that host may be in. On a router, you can actually go in there and see the routing table. Even Windows systems, PCs can be routers if you choose to configure them as such. We hardly ever do this. Usually routers are appliances like a Cisco router or an Terasys or an HP or something like that. Even Linux can act as a router if you were to do so. Well, within all these machines, all these appliances, I can look at the routing table. Right? On a Cisco device, show IP route will give me what's in RAM, and here's the routes to everywhere that it knows. Now, don't expect this to be, we're not going to go into too much detail here. We have CMIT 225, the routing and switching class, which we go into detail on this. We deep dive and configure routers and configure these environments. Our purpose here is really just to become familiar with it. But when you see something that looks like this, a routing table, that belongs to a router, and that shows its roadmap, where it goes to. Now, I mentioned that they choose the best path, right? Sometimes there's only one path data can take. There's only one path a router can go. And in that case, it doesn't have a whole lot of decision making to make. But a lot of times, there's multiple paths. Well, how does the router figure that out? It does something using metrics. And it bases its metrics on a variety of different things. Things like hop count, which is the number of times the packet will have to cross a router before it reaches its destination. It can do things like bandwidth or throughput, right? Network performance, latency. It can measure that on the line in some cases and make decisions based on that. The topology of a network. What's topology? It's a map. So routers could be programmed with different sets of rules in there based on certain network topologies, hop counts, bandwidth restrictions, all that. Now, for exchanging routes, the whole idea, how routers learn about where things are, is that they have to populate their routing table. They have 2 ways of populating their routing table. It can be done statically, which means, and this is a human being, network administrators sit down and we type into every router which route is which. Right? We tell it, hey, if you want to go to 192.168.1.network, you go that way. If you want to go to the 10.1.2. network, you go that way. And the routers just make their decisions based on what we told them. We can also have something called dynamic routing, where we let the routers talk to each other. Effectively, we let the routers gossip to each other, and then they exchange routing information. So humans don't. We set up the routers, we set up the routing protocol, but then from there the routers take care of it themselves. So what's better? Why two different technologies for different purposes? In high security environments, banks, that type of thing, they're probably going to go with static routing, because static routing is set by a human being and it's arguably more secure. However, its downside is that it doesn't scale well. When you start getting into big environments and you're having to statically set your routing information on all your routers, well, that can get pretty untenable pretty quickly. And if something changes, your routes are going to break until a person goes in there and fixes the routing tables. In dynamic routing, this could scale quite largely, actually. That's the whole point behind it, to build big environments, big networks, and let them exchange their routing information and just keep the thing running. Downside to it? Well, it could be a security risk. I mean, what am I doing? I'm advertising all my the map to my network, really, along my network. So if somebody was trying to hack me or trying to gain access to me, and they were able to read my dynamic routing information, I'm kind of giving them a roadmap. I'm giving them a roadmap to my house so they can come and rob me. So there's a potential downside there. A potential upside is that it'll automatically fix things. So I got a connection between two routers, and let's say the cord gets cut. Well, under a static routing protocol, the routers won't know about it. They're going to try to send information down that route. It's not going to work. I'm going to lose what's called convergence, or the ability for my network to completely communicate with itself. Using a dynamic routing protocol, they'll quickly figure out, hey, this route's not there anymore, and calculate a new one and exchange it among themselves. This exchange, this gossip I talked about, is what's known as a routing protocol. Okay? And there's several different routing protocols. We're going to look at them. And there's some terminology that's common really to most of them. And we have this thing called, the first one is this thing called administrative distance. And it's simply a numerical value that defines how reliable that routing protocol is. Some are more reliable than others. It's kind of like if my wife tells me something and my kids tell me something. I'm going to believe my wife before I believe my kids. My wife has a lower administrative distance than my kids do. And the lower the AD, the better. So my wife has a distance of 1. My kids have a distance of like 400. So anything that she tells me takes precedent over what my kids tell me. Well, that's how AD works between different routers. I might have one routing protocol with an administrative distance of 90 and another one with an administrative distance of 120. My router will trust the 90 over the 120. Convergence time. I mentioned convergence. It's where all parts of my network can talk to each other. It's where everyone's talking on the same page. They've all exchanged their routing information, and we're good. We have full communication across our network. It takes time to reach convergence. And different protocols reach it in different periods of time. Some are chattier than others. Some take longer. It all comes down to what we need out of our routing protocols. And then overhead. Some routing protocols require more number crunching than others. More number crunching means I need a more powerful router to be able to process it. And we have a variety of protocols right here. We have RIP version 2, OSPF, ISIS, BGP. These right here, the first 4, are what's known as interior gateway protocols. Right? And they're used for inside our environments, right, by interior routers. So if I want to use, if I have a small network, I might get away with something like RIP, the routing information protocol. If I've got a larger environment, I might need to use one such as OSPF, which is a interior gateway protocol, but is able to scale much larger. No, any of those protocols, though, they're interior protocols also, only. I also have exterior gateway protocols, or more specifically, a exterior gateway protocol. These are protocols that live on the internet, that route between LANs. And right now, there's only one of them, Border Gateway Protocol. Now, as a network administrator, CCNA type person, you're not really going to be messing with this. Border Gateway Protocol is more of an ISP type of thing. When you start getting into CCNP, CCIE level type of things. But within your own environments, you will certainly be using some type of routing protocol, most likely. It would be great if routers always worked, but unfortunately they don't. Well, we have tools that allow us to help us troubleshoot our routers, or what's going on with our routing protocols. Last week, we actually introduced ICMP, right? Our Internet Control Messaging Protocol. That's that layer 3 protocol that gave us ping. Remember that? Well, we have ICMP also includes other tools in addition to ping. Probably our most useful one is called Traceroute, and this really focuses on routers. Let's take a look at it. I got two nodes right here. Here's my source, here's node A, and there's my destination node right there, node B. And we communicate back and forth. Well, all of a sudden, communication breaks down, and I want to try to figure out why. I could use just a ping command, and I could say, hey, node A, ping node B. And what happens is it sends that ICMP packet through the network, hits the destination node, and then it echoes back all the way back through. So I see reply from, reply from, reply from, or no reply received, no reply received, no reply received if it can't communicate with it. Ping is incredibly useful, but it only tests the end devices. Right? I don't know what's going on in between here. Traceroute, and all operating systems, all common operating systems, have some version of Traceroute, including our router operating systems. What Traceroute does, it's like a ping, except it's also pinging every device on the way to the destination. So from here, I would do Traceroute node B, and the first packet, it would go to each hop, and remember, each hop is each router the packet encounters on along the way. So in this case, this is a 2-hop path. Hop 1, hop 2, destination. Traceroute pings this first router it encounters, and I get a reply. And then it goes to the next hop, pings that router, and I get a reply. And finally, it goes all the way through, pings my destination, and I get a reply. So I end up with this little map showing me the path my ICMP packet took to get to its destination. Why is this useful? Well, if I can't ping host B using a ping command, how do I know what the problem is? Is the problem between me and the first router? Is the problem between this router and that router? Is the problem over here? You don't know. All you know is I can't talk to my target. With Traceroute, it helps me break it down. So if I get a response from my first router, but no response from my second router, I know my problem is over here somewhere. Likewise, I get a response from my second router, but nothing from my destination. Well, I know that the routers are good. My problem is over here. Maybe my actual destination node itself, or maybe the cable got cut over here or something. It helps you narrow down where problems lie, and is totally useful. There's other tools out there under ICMP and under IP and various user shells that we can use to troubleshoot things. We already looked at ARP, right? That'll show us our address resolution protocols, Traceroute. We can do an ipconfig or an ifconfig if I'm running a Windows or Linux systems to look at what my IP settings are. Obviously, I can ping. That always comes in handy. DNS lookup, I can query my DNS server, see if hostname resolution's working, all that. We have a variety of utilities that we can use to troubleshoot our networks. And it's our job as network administrators to find problems and fix them. And with that, that is a wrap for our Week 4 lectures. As usual, if you have any problems, any questions, please reach out to me, and I will see you next week.